So once again, when I don't have a number there, it's understood to be a value 10, which is once again your calculator. This is your calculator. Well, if I take the log of 1, Grant, what do you get?
0.
10?
1.
2? 100?
2.
1,000?
3.
Okay, 10,000.
4.
100,000?
5.
Keep going.
6. 7.
6 and 7. So if I take the log of these numbers, I get some nice whole numbers there. Well, the question is, where do these numbers come from? Well, let's take a look at our numbers here and the values that we took the log of. What is the relationship between the numbers that we came up with and the numbers we took the log of? Okay, so when I took the log of 10,000, well, 10,000 has 4 zeros. My answer was 4. 1 million, I have 6 zeros here. So that's log of 6. If I took the log of 1, I have 0 zeros there. So I have 0. Here I had 1 0. Well, let's take a look. How do we get zeros at the end of these numbers? If I would take 100,000 here, what can I multiply to get 100,000? What's an easiest way of getting 100,000? Well, yes, I can multiply 1 times 100,000. I get that. But if I take a look at a series of numbers that I can multiply together to get 100,000, how many times would we have to multiply 10 by itself to get 100,000? Or how many times would we have to multiply 10 by itself to get 1,000? Well, every time we multiply by 10, what are we adding to our number? A 0. So when we multiply by 10, we add a 0. So this means I've multiplied 10 times 10 times 10. Because I multiply by 3 zeros there. Give me 3 zeros here. 1 times 1 times 1 gives me the 1. Over here, I'm multiplying 10 times 10 times 10 times 10 times 10. Because every time I multiply by 10, I add a 0. My 1 times 1 times 1 times 1 times 1 gives me the 1. But each one of these zeros goes a 0 at the end. So it tells us how many times we've multiplied 10 by itself. So if I multiply 10 to the 7th power, 10 to the 7th power, I would get 10 million. So it tells us the number of times we're multiplying 10 by itself. Well, once again, where is the 10 at? Well, if I take a look right here, here's my 10. And in the logarithm form, this is called log base 10. Log base 10. Well, if I have a number to an exponent, here's my exponent. What is the 10 called? The 10 is called a base. If this is our exponent, if we say we have to have if we have an exponent, we have to have a base. We have to have something there to tell us how many times we're going to use it as a factor. Because if I just say we have a value of 7 and say I have an exponent of 7 there, well, that doesn't look like an exponent of 7. Why? Because I don't have any number underneath it. So we have to have a base for it to be an exponent. Which now gives us a relationship between a base an exponent, when we take a base to an exponent, we get some value. If I take a base to an exponent, I get some value. If I take 5 to the third power, I get 125. That's my value. I have a base of 5 and an exponent of 3. Which now allows us to be able to make a nice little conversion. And this goes both ways. If I have a to the x is equal to b, a is my base. So this is log base a of b is equal to x. Bless you. Whenever you solve an exponent problem, this is a key idea to remember. When you're finding a logarithm of a value, your answer is going to be an exponent. Your answer is an exponent to the base of the logarithm. So when you're finding a log of a value, when you hit the log button on your calculator, your answer is going to be an exponent. Well, if you have an exponent, you have to have a base. The base is the base of the logarithm. So we have base, we have exponent, we have a value. Once again, this is a key relationship to remember. We have a log with a base of some value is equal to an exponent. Once again, knowing this relationship is going to help you solve logarithm problems. Because logarithms tend to be somewhat still a mystery to us. Okay, if you don't use them on a daily basis, they become a mystery. Okay, the mystery mathematical operation. But if I can convert this into something that's a little bit more familiar to me, it's a little bit easier to work with as we go through some problems here. We have a common log, which is log base 10. This is called a common log. It's your calculator log. It is your calculator log. You also have what is called a natural log, which is a log base e. Once again, log base e. Base e is Euler's number. This is your log base e, which is your ln. Log natural. Log base e is your ln. You also have an ln button on your calculator. Domain for logarithm. Well, try to take log of negative 10. Take the log of 0. Can you find values? Nope. Well, these will give us an empty set. These are undefined. So we cannot take the log of negatives. We can't take the log of 0. But we can take the log of any positive value. So when we're talking about a domain, we're talking about the domain. This value, and this is log base anything of f of x. This base can be anything. It does not matter if this is 2, 7, 9, 14, 25, e does not matter. Pi, this f of x has to be greater than the value of 0. So what would be your domain for the next two? Put in an interval notation. That creates somebody around you. Justin, what do you have for the first one?
XE parentheses 3 to positive infinity.
Okay, 3 to positive infinity and beyond. As 2x minus 6 has to be greater than 0. So I add my 6 over, divide by 2. X has to be greater than 3. Second one, what do we have for the second one here? Marley, what do you have for the second one? X is greater than 7, so we're going to subtract 7. Subtract 7, so we have x is greater than negative x is greater than negative 7. So we have to do what? Divide by negative 1. When we divide by negative 1, what do you have to remember to do? You divide by negative. Turn that thing around. So we have x less than the value of 7. So we have negative infinity to 7. And we're open at 7. Log base 2 of 32 is equal to some value. We want to find this value. Well, here's my suggestion. Once again, by trying to find a value, throw an x in there. That's what we want to try to find. We want to solve for x. But in this form, it may be a little bit more of a struggle with our brain because we're not so commonly used to using logarithms. So let's take it out of the logarithmic form and write this into an exponential form. Well, if I was writing this as an exponential form, what would it look like? I have log base 2 of 32 is equal to x. I have a base of a value is equal to an exponent. What does that look in an exponential form? Okay, I have it in logarithmic form. I want to write it in the exponential form. What would it look like? Paige, what would that look like?
2 and then x is the exponent equals 32.
Okay, 2 to the x is equal to 32. We want to find what x is. Now, this we feel a little bit more comfortable with. How many times do I have to multiply 2 by itself to get 32? Well, I use my fingers a lot. 2 times 2 is 4. Times 2 is 8. Okay, I count them up. Rachel, what do you come up with? 2 to what power is 32? Five. Value of 5. Write it exponentially. Okay, put an x in there. We don't have anything there, put an x in there. So once again, you can write it into an exponential form. Sarah, what do you come up with?
X equals 2.
X equals 2. Where we have 7 to the x is equal to 49. What exponent do we need to take 7 to? Well, how many times I multiply 7 by itself to get 49? 7 times 2, or 7 to the 2th power, 49. Solve the next two. Try to solve the next two. Check your answer with somebody around you. These will tax you a little bit more with your properties of exponents. In the first one, if we have 5 to the x is equal to 25, my x value would be 2, because 5 squared would be 2. But what I'm doing is I'm putting that process in reverse. I have 25 to the x is equal to 5. So what do we have to do to 25 to get ourselves back to 5? Ethan, what would you do? Exponent 1/2, because we would have to take the square root. If we would take the square root of 25, we would get our value of 5. Well, if I'm talking about a square root, my square root exponent is the value of 1/2. The second one over here, 2 to the x is equal to 1/8. Well, if I just had 2 to the x is equal to 8, Grant, what would x equal? X would equal a value of 3. So what we have is 1 over 2 to the 3rd power. Well, once again, how do I put this into a value up here? Well, what do we have to do to bring this value up top? Nolan, what do we have to do?
I don't want you to decide.
Huh?
Make the exponent of 3 negative.
Okay, so we have 2 to the negative 3rd, so we have negative 3 is our value. Once again, we can't do this on our calculator because these are different bases. This is not log base 10. Okay? If we take a look, these are all different bases. So if I have something that's not 10, I can't sit there and click it, clack it into my calculator and just take the log of 32 or the log of 5 because I have a different base other than 10. Your calculator is only a base of 10. So let's start solving some equations. we have log base 5 of x plus 5 is equal to 2. In this form, it's not solvable. So this is taken out of this form into an exponential form. Once again, we have log base b of some value is equal to an exponent. That's the same as base to an exponent is equal to value. Our solution, the solution, once again, when dealing with a log problem, when you're trying to find the solution of a log problem, the solution is an exponent. Your solution, so when you're talking about solution, whatever you're equal to is the exponent. The base is the lower number underneath everything. So Cindy, guys, if I was writing this into an exponential form, what would it look like?
X plus 5.
What's my base and what's my exponent? This is my value. This is my value. 5 is what? Okay, so we have 5. What's our exponent? I'm sorry, I can't hear you.
2.
2. Okay, so here's my base, here's my exponent, here's my value. Base, exponent, value. So I have x plus 5 is equal to 5 squared. Now we can solve the equation. X plus 5 equals 25 and subtract 5. X equals 20. Go to the next one, solve the next one. What's my base, what's my exponent, what's my value? Take your answer, somebody around you. Typically, what I deal with, I look at, here's my base, here's my exponent. So I always put that first. Because I go base, exponent is equal to a value. So we have 2 to the third is equal to 2x minus 6. Janae, what do you get for x? X equals 7. Go with that. Gives me 8 here. Add your 6 over, so we have 2x equals 14. Divide by 2. Base, exponent, value. Difference with this one, though, this is going to give you a quadratic equation, which means you need to now solve a quadratic equation, which needs to factor down, get it equal to 0, get your equation equal to 0, and then factor it down. Okay, what do you come up with?
-9 and +1.
-9, +1. Okay, we factored x plus 9, x minus 1. Okay, now what we need to make sure we check, we should have checked the first ones up here. We need to make sure that when I put my values in, I don't get a negative value there. Here I have 14 minus 6. I'm positive with my 8. If I put -9 in here, I get positive 81 plus a negative 72. I'm still positive there. If I put 1 in there, I get 1 plus 8, which is 9. I'm okay with that. Okay, set up and solve. This will be a little bit more challenging for you. Think about how you can write a square root as an exponent, and let's get 27 as a base of 3. What would that be? Let's go back to what we just did yesterday. Square root would be 27 to the what power? And then rewrite 27 as a base of 3. Jacob, square root's what power?
Third.
Square root is what power?
Second.
How can we
Oh, wait, half.
1/2. Then 27 we can write as 3 to the what power?
30.
So we have 3 to the third to the 1/2. We have a power to a power. What do we do with our exponents when we have a power to a power, Cindy Miller? Multiply them. So we have 3 to the 3/2's power. If my bases are equal, my exponents must be equal. If your bases are equal, exponents are equal. So x then would equal 3/2. Go down the bottom one here. Log base 4 of log base 3 of x is equal to 0. Let's work ourselves outside in. Here's my base, here's my value, here's our exponent. So we have a base of 4, our exponent of 0, and here's our value. 4 to the 0th power is a value of what? 1. So now rewrite log base 3 of x is equal to 1. So we should have 3 to the 1th is equal to x. I have a base, I have an exponent, I have my value. So I have base exponent, 3 to the 1 is equal to x, so x is equal to value 3. The key thing to be able to do is how to get it out of this form in the logarithmic form into this. Because in the logarithmic form, once again, it's still somewhat of a to us. But into an exponential form, we feel a little bit more comfortable in an exponential form. Okay, we still may be not great at it, but at least in an exponential form, I have something I could go back to. I have some basis in my mathematical repertoire from my years past, where I can use my properties of exponents. So you have problems to deal with basic log problems, and then you have some equations to solve on the back. You have some domains on the front here. Monday we'll come in, we'll deal with properties of logarithms. And then Tuesday will be more or less like a worksheet. Wednesday will be review. Thursday we'll have as a test over logarithms. Okay, Friday will be a preparation day for a final. Okay, we'll get our final in before we go to Christmas break, which I think will be beneficial for you. And that's the reason why we'll push here, because I'm trying to get things that are beneficial to you, okay, with respect to your grade. Because sitting around for 2 weeks and not thinking about math, you lose a lot. Questions? All right, QED has done. Gracias.